Hello, my name is Rikako Kono, and I am an MPhil student at the Australian National University. Today, I'm going to talk about our mathematical models for off-board scoring prediction in basketball, which has been collaborated with Keisuke Fujii in Nagoya University. Okay, first, as an introduction, I'll talk about the current situations around studies on invention games. In invention sports like basketball, soccer, and hockey, it's crucial to consider both onboard and offboard movements. Onboard movements are the actions around the ball and naturally gain attention because it's not the support. However, offboard movements which occur away from the ball are also important since they significantly impact the game dynamics by creating space and disrupting the defensive structure. Despite their importance, studying off-board movements is challenging due to the complexity of the spatial-temporal tracking data. Several studies have attempted to address this, such as the work by Seven et al. In 2016, developed a framework to estimate the number of points obtained through the position, called expected position value, EPV. Now, I'd like to introduce our basketball model via MOS, which stands for ball intercept and movement for off-ball scoring. This is a mathematical model designed to estimate the probability of scoring in a subsequent event. By mathematical model, we mean that we realistically modeled both players and ball movements as depicted in the right figure. This allows us to understand complex game dynamics in an intuitive and interpretable way. We developed this model by leveraging sports VU and VA tracking data from the 630 games in the 2015 to 2016 season. We used 580 games for training and another 50 games for testing. The video you see here shows the resulting BI-MOS distribution over a basketball court. This is our game between the Toronto Raptors and Charlotte Hornets from 1st January 2016. Okay, then let me now explain the background and concepts of our model. Our model is extended from the off-board scoring opportunities model called the OBSO model. This was introduced by William Spearman in 2018, and as you might know, it's designed to estimate the probability that a pass to an arbitrary position on the soccer field will result in a score in a subsequent event. In extending the OBSO model to basketball, we not only adapted the concept of pass to score situations, but also incorporated situations that were not explicitly addressed in the OBSO model, which is the dribble to score situations and the ball interceptions. Okay, here is an overview of our model structure. The BI-MOS model consists of two components: the potential ball control field model, called the PBCF model here, and the scoring probability. The PBCF model, illustrated in the left picture, is the probability of the attackers maintaining position as they deliver the ball from its current position to the target position. We've distinguished between pass to score and dribble to score situations in PBCF, as shown here. In the middle, we have the score model, and it calculates a simple scoring probability based on the distance from the basket. Here, we assumed no defensive pressure. We fit scoring probability with exponential function as shown in the bottom right graph, and expanded it to cover the entire left half court. By multiplying these two models, you can get the BI-MOS distribution as presented on the right. Okay, then I'll go into the details of the PBCF model. In the PBCF, we think of situations like the right picture. The ball in black is moving towards an arbitrary target position L, either through a pass or dribble. And time t already has elapsed since its movement started. Both an attacker in red and a defender in blue are heading to the ball. To get the total PBC value for player I at the target position L is numerically calculated by integrating the player I's infinitesimal PBC value for from the beginning until the ball reaches the target position. In the calculation, it's like that. Integrating from 0 to t-calc here is the time when the ball reaches the target position. Each infinitesimal PBCF, I mean the inside of the integral, is calculated by multiplying the function f in blue here by lambda in green. The function f offers the probability that player I will lose the ball position before the ball, by time t. I will elaborate on this in the next slide. Meanwhile, the lambda here represents the speed at which a player can gain full control of the ball upon reaching it. As you can see, lambda is the inverse of the time taken for a player to establish full control. Thus, a higher lambda value means better ball control skills. And also, defenders might not need full control. So to account for this, we adopted the adjustment parameter kappa, which is greater than 1. Okay, I'll explain the details of the function f, which is the probability that player I will lead the ball position by time t. This function is constructed by calculating the residual between the true time and the expected time for a player to reach the ball. By calculating this residual, we can get the probability that a player who is expected to reach the ball position by tau expected actually arrives by tau true. Therefore, by substituting tau true with t, this accumulated function becomes the function f. Before discussing the shape of this function, let me explain how to calculate tau expected. First, we assume that player moves with uniform acceleration with an initial velocity. And we also set a realistic upper velocity limit to 5 meters per second. So it's typo. Also, we took into account the reaction time required for players to change their direction. Secondly, we assume that the ball moves at a constant speed. The ball speed is adjusted based on the travel distance and whether a pass or dribble. In the bottom right graph, the x-axis is the travel distance and the y-axis is the ball velocity. And you can see how it varies depending on the distance and the situations. As you might notice, the resulting residual function has a positive tail along the x-axis, and it follows a symmetric Lorentzian function. This indicates that in reality, it often takes more time to reach the ball position rather than a simple uniform acceleration model, and which aligns with our intuition. Other factors that might affect tau true, such as tracking data inaccuracies or tactical decision making, are not explicitly taken account here, but the function f would include these vague aspects. In the final phase of our model construction, we estimated parameters that are difficult to derive from the data, such as the player's constant acceleration, the reaction times for both attackers and defenders, and the control rate parameters lambda and kappa. To estimate this, we employed the maximum likelihood estimation technique using the nailed-mead algorithm. In the likelihood equation shown here, P represents the BRMOS value and Y represent the result, where Y equal 1 for score and Y equals 0 otherwise. For the BRMOS value, we use value calculated when players passed the board in the pass to score sequences, and when player began dribbling in dribble to score situations. For example, in the left picture, this ball possessor passes to this player and shoots. So I selected this value. Whilst in the right picture, this ball possessor dribbles to this position and shoots. So I selected this value. So we initialize the parameters as shown here, and the resulting values are presented here. So one noteworthy result is the reaction time, I guess. The attacker's reaction time is shorter than the data's defenders. This aligns with our expectations as attackers are likely to react more quickly to ball movements because they usually share the team's tactics. Using the estimated parameters, we constructed our model and plotted the actual score versus the expected score per game using 50 test games for validation. The left graph displays all situations, and the middle one only for the pass to score situations, and the right one is for the dribble to score situations. Overall, it's safe to say that our model will estimate scores, which supports its validation. However, when you see the coefficient of determination values here, the dribble to score shows a slightly lower value, which suggests that we might need to develop a distinct model for dribbling situations rather than applying a similar approach as we do for passing. Here, I'd like to note that the score prediction is done just for validation, and it is not the main main application of this model. Okay, our work on application is still developing. First, of course, our model can be used for tactical review, as shown in the left picture. In the scene, the player with the ball here dribbled to this point and resulting in no score. However, according to our model distribution, a pass to the player on the right or left would have offered a higher scoring expectation. I believe this aligns with our expectations of the game. In addition to tactical review, it could be used for player evaluation, particularly in assessing spacing and positioning. First, for instance, the average BRMOS value per scene for each player can serve as a metric to indicate how well players maintain high score expectation areas. Furthermore, when you want to evaluate a player's space-making ability to create space by drawing defenders, you could compute counterfactors by calculating the BRMOS value if the player were in a different position and comparing it to the actual score. These applications will be tackled in our future work. Okay, in summary, our model provides an intuitive and effective approach to estimating scoring probabilities in basketball. However, there are several limitations that we plan to address in the future. Specifically, we aim to modify the score model to incorporate defensive pressure and also develop a distinct model for dribble to score situations, and also account for the impact of 2-point and 3-point shots, which is a unique rule for basketball. Additionally, our future work will focus on developing valid indices for player evaluation, as mentioned in the previous slide. For your reference, I've included a QR code for our archive and GitHub here. Thank you for your listening.